All right, so we're going to take a look at 3.3, okay, which is on the factor theorem. So factoring has a lot to do with division, right? Division is one way to figure out a factor to something if you don't know it. And I'm going to go through an example of that right now. So remember that if I ask you to find zeros or I ask you to find roots to an equation, what I'm asking you to find is a value you can plug in for x, and the answer comes out to 0. And this statement with IFF, it's kind of from geometry. It means you can read something forward and backwards, and it's true both ways. And it says that if you have a number that's a root, then when you plug it in, you'll get 0. The other way you can read it is, if you have a number you can plug in and it gives you 0, then that number is a root. So you can read the statement forwards and backwards. That's what IFF means. It's an abbreviation for if and only if. In geometry, you probably learned that as the statement and its converse. Say, Mike. So we're going to look at using long division to figure out factors or to find roots. We've learned before that if you can factor something, bless you, it makes it a lot easier to find the roots. So for example, if I gave you this and said quickly, tell me the two numbers you can plug in to get 0, you probably can't do it in under a half a second. But if I write a factor as x plus 1, x plus 3, now I can say -1, -3, done. Very, very quick. Okay? So if you can factor something, it makes it easy to find the roots. That's why we do it. So let's say I wanted you to factor the number 12. Okay, this is an example with numbers before we get into doing it with a polynomial. If I want you to factor 12, that means I want you to write it as something times something. Now, I'm going to tell you that 3 is a factor. How could you find the other factor knowing that 3 is a factor? Yep. Right. You could take the 12 and you could divide by the 3 because you know 3 times something is going to give you 12. So to figure out what the something is, divide both sides by 3 and you get 4. And that tells us the other factor. So we had to use division. We didn't use long division, but we used division. The important thing to notice is if you know that a number is a factor, when you divide it, you will get a remainder of 0. If I tried to divide 12 by 5, I get a remainder, right? I get a remainder of 2. That means 5 is not a factor of 12 because you get a remainder. So remainder of 0 is going to be a really big idea in this section.
Right, sorry, if you do what? Did you know for remainder of 0?
If you know that a number is a factor of another number, then when you divide it, you should get a remainder of 0. Like if I pick 24 and I divide by 8, I know 8's a factor of 24, so 24 divided by 8 should give me remainder 0. And it will. So basically what I just said to you guys, that if you divide two numbers and you get a remainder of 0, you know that the number you divided by is a factor of the numerator. And the whole point of being able to find a factor of something is to be able to find the roots. Factoring makes it super easy to find roots. Quadratics, we know how to factor. So you might say, well, why do I need to learn about this if I can just factor a quadratic by trial and error and eventually get the answer, if it's something that's factorable? Well, when we get into something that's maybe a cubic polynomial and you have to factor it into 3 sets of parentheses, you're not going to be able to just guess and check the answer like with a quadratic. It's too complicated to do that. So we have to get into this long division idea. And I'll show you how it works. So that process that I just showed you, we can do exactly the same thing with a polynomial. What I think I'll do first is I'll give you the steps for how to do long division. Sometimes I do an example at the same time, so you can see a step and then see how to do it. Sometimes I just give all the steps first. I don't know. I'll give you a step and then we'll do the step. So I think it's going to be 5 steps. So what you probably want to do is leave enough room to write 5 steps. None of the steps are that long, but about all the same length as that step. So the first thing we have to do is if the dividend is missing any terms, every term has to be represented, even if it's a 0 term, because we're going to be putting things in columns. And if we don't have a column for every single power, then we're going to get messed up. Yeah. So the dividend, that's what's under the root. Okay, the divisor is what's on the outside. Just in case there's any questions about vocabulary. So let's look at an example and see if we can do that part first. I know it's kind of small, but that's x minus 3 as a divisor. And we're dividing it into x cubed minus 8x plus 3. The first thing I'm going to do is rewrite it. And I have to represent every power from the highest to the lowest. So x cubed is the highest. What should I put as my next term?
0x squared.
I need to represent the squared terms. And I was missing that. So put plus 0x squared, and then the linear and the constant, those are all set. That's step 1. Any question on step 1? Step 2. Divide the first term of the divisor into the first term of the dividend. So if you want to think about what you're doing here, kind of off to the side, you're doing this. X cubed divided by x. You're dividing, excuse me, first term of your divisor into the first term of the dividend. What is x cubed divided by x? X squared. Doesn't matter where you put this. Just put it up above the line anywhere you want, because what's above the line is going to represent our answer. So we have x squared. And that's step 2. Now, step 3 is basically checking the answer you just did. So we're going to know if we did it right. Multiply the answer that you just got. This says multiply the answer from step 2 by each term in the divisor. Sounds like a distributive problem. Multiply the answer from step 2 by each term in the divisor. And this is where it's important to line up like terms. Put the result under the appropriate term. What I mean there is make sure you line up like terms. Right, so let's multiply the answer from step 2 by each term in the divisor. What's x squared times x? X cubed. Put that under the x cubed. What's x squared times negative 3? Negative 3x squared. And that's all you do for step 3. Multiply each term on the outside by the answer that you just got from step 2. Questions on that step? Step 4 is subtract. Subtract the columns that you just made in step 2. And when I say subtract, I mean this. Both columns get subtracted. So we have x cubed minus x cubed. What's going to happen there? That's going to cancel out. If that doesn't cancel out, you did something wrong.
What was step 4?
Step 4 is subtract. So we divide, multiply, subtract, and then bring down is going to be step 5. But we'll get to that. So we subtract those. And what's 0x squared minus 3x squared? 3x squared. So you have to remember when you do this subtraction, you're doing it to both numbers. X cubed minus x cubed. 0x squared minus 3x squared. And then step 5 is bring down the next term and repeat. So the next term is minus 8x. Now, look at the highest exponent that I'm left with now. What is it at this point? It's a 2. It started out as a 3. Each time you do this one round of division, that's what we basically just did, like one round, this exponent should drop. It should drop. Usually it drops by 1 each time. It can drop by more than 1 in a special case. But the goal is to keep going until this exponent is less than that exponent. So keep going until you either get a remainder of 0, then you're definitely done. Or if you don't get a remainder of 0, until the degree of this number is less than the degree of that number. Okay, so now we'll repeat steps 2 through 5 until we're done. So now divide x into 3x squared. What do you get if you divide x into 3x squared? 3x. Multiply it back out. Kian, what's 3x times x?
3x.
That should always happen because that should cancel. And what's 3x times negative 3? And this is why I had to bring down the 8x, so I keep everything lined up in a column. Subtract. Going to notice with long division problems, the work goes down and to the right. So don't start a long division problem on the right edge of the page, because that's where you need to put your work. All right, what happens when we do 3x squared minus 3x squared? Cancel. What's negative 8x minus 9x? X. Now the degree is a 1. The degree here is a 1. Well, now they're equal. We got to go one more time. Bring down the 3. What's x divided into x? 1. At this point, that's your quotient. If that's all you wanted to know, you're done. There's your quotient. Let's finish it off to get our remainder. So multiply 1 back out. What's 1 times x? 1 times negative 3. And you might think, ooh, plus 3 minus 3, remainder 0. That's great. But be careful, you're subtracting. X minus x is gone. What's 3 minus minus 3? 6. That's my remainder. So a couple ways you can write your answer. The quotient is x squared plus 3x plus 1. And the remainder is 6. What does that mean about x minus 3? Because when I divided it into this polynomial, I didn't get a remainder of 0. X minus 3 is, it's not a factor. If you were trying to factor this cubic, x minus 3 is not 1. You can't just spend all day guessing. Let's try x minus 2. Let's try x plus 5, x plus 6, x plus 10, x plus 9. You don't want to just keep guessing. There's a way to figure out what it is.
Sorry, can you scroll back down for the last few steps?
Okay. So when we're looking at the quotient and the remainder, that's one way you can write the answer. Here's another one. Okay? And this way comes from, just think about with numbers. If I took, say, 17, and I divided by, let's say, 5. What's the quotient here? 3. And what's the remainder? 2. So another way you could write that answer is quotient plus remainder over the original denominator. 3 plus 2/5. Or we could say the answer to that problem is 3 2/5. Quotient plus remainder over the original denominator. So let's do the same thing here. We could also write the answer is quotient plus my remainder over the original thing I was dividing by, over my divisor. Divisor, denominator, same.
Why would we write those in that way?
Just a different way to write the answer. Just depends on how they want it.
We're going to do another example similar to that.
Yeah. But both of those are exactly the same. Quotient, remainder, divisor. Just like you would do with, 17 divided by 5. The nice way about the second one is you can type that in on y1 on a graphing calculator. You can type the original problem in on y2, and they should look identical. And then you know your answer is correct. Any question on that? All right, let's try get another long division one. This time isn't set up for us properly, so we can start right away.
Yes.
Yeah, they filled in the zeros for us. If you didn't, first thing you want to do. Okay. Take the first term of your divisor and divide it into the first term of your dividend. So off to the side, you should be thinking about doing this. What's 2x to the 4th divided by 2x squared then? X squared. Now multiply the x squared back out. What's x squared times 2x squared? What's x squared times x? Notice I put it under the x cubed. And what's x squared times 1? X squared. And what do we do with all those columns? Subtract them. Okay, 2x to the 4th minus 2x to the 4th, that's gone. What's negative x cubed minus x cubed?
Negative 2x cubed.
Okay. And what about 0x squared minus x squared?
Negative x squared.
Okay, so we got that. Bring down your next term. Do it again. The exponent was a 4. Now it's a 3. Keep going until it's smaller than a 2. And then you're done. Okay. Yep. What's negative 2x cubed divided by 2x squared? Negative x. Okay, you're going to know if you did it right because you're going to check it right now. What's negative x times 2x squared? and negative x times positive x.
Oh, negative x.
Negative x squared. And negative x times plus 1. Negative x. Watch what happens here. What's negative 2x cubed minus negative 2x cubed? What's negative x squared minus negative x squared? We're done now. We just got two things to cancel, so this exponent is going to drop down to a 1, which is less than 2. So we're done. We just have to finish the arithmetic. 0x minus minus x. Bring down your last term. That's your remainder. Okay. So one way you could write it, quotient, x squared minus x, remainder, x minus 2. Or you can write it the other way I showed you as well. Quotient plus remainder over original divisor. The thing I like about the second way is you can type that in on your calculator, type in the original problem on the calculator, and see if the two graphs look identical. If they don't, then something's wrong. Yep.
And then for the problem that we did at first, our remainder was 6, and that had an exponent of 1, but then I thought the divisor's degree was 1 as well? I'm not sure.
So in this problem, the degree on our remainder is 0. Because we ended up with a constant.
Oh, true.
So this degree is a 0.
Okay. That makes sense, thank you.
Yep. And this degree originally was a 1.
Okay.
On this problem, the degree on our remainder is a 1, and the degree on our divisor was a 2. 1 is less than 2, so we're done.
Wait, okay, alright. I'm a little confused. What is the term that you're consistently dividing by?
This is what you're dividing by. This would be like your denominator. It's your divisor. If you think about it like this, like if you did 3 into 12, that means to do this number on top, the number on the outside goes on the bottom. So 12 is like your numerator, 3 is your denominator.
Okay, and then are you multiplying it by the first term that you find?
So once you find a term, you're distributing it back out to everything.
And then you use that.
And then, right, then you put that below in your columns, subtract them, and then you divide the first term by the first term here. And then you get another term, and then you distribute that out and do it again. Once you understand the algorithm, it's the same thing every time. We might do one more. I don't know if we'll get to another one, but we certainly can practice some when we do our homework. So this is another thing that makes a lot of sense if I just write it with numbers. It'll help it make more sense. But it says, let's say you had two polynomials, f of x and h of x. If you divide the two of them, you will get a quotient and you will get a remainder that satisfy the following equation. Your numerator equals your denominator times your quotient plus your remainder. This is how you check your answer when you learn to do long division, back in like 3rd grade or whatever. Let me make something up with numbers. Let's do 17. Let's let this be, actually I think I did that, let's do 18. So 18 and 5. If you divide 18 by 5, what do you get? Oh, I don't want to have two numbers that are the same. You can have the quotient and remainder the same. I just think it'll make it more confusing. What do you get when you divide 17 by 5 for a quotient? 3. And what do you get for a remainder? 2. So let's see if it satisfies this equation. What was f of x? 17 equals, basically checking my answer. What did I divide by? 5 times, what was my quotient? 3 plus what was my remainder? 2. 5 times 3 is 15. 15 plus 2 is 17. That's how you check your answer with long division. We can do the same thing with a polynomial. It's what you divided by times your quotient plus your remainder should equal the original numerator. If it doesn't, you didn't do something right.
Okay, alright. And for the 17 and the 5, those were just made up numbers for this scenario.
Yeah, and I made it up with numbers because it's a lot easier to see how this formula works with numbers than to do a full-blown problem with letters. But it's the same idea. So remember that the degree of the remainder has to be less than the divisor. I'm just reminding you, that's how you know when you're done with the problem. Okay? Or, it goes in evenly, you get a remainder of 0, then you're definitely done. So remember that. Whatever you're dividing by, your remainder has to be a degree less than that. So if you divide it by something linear, what's the degree? Doesn't matter what's in the top. What's the degree of something linear?
1.
Degree 1. So if you divide by something linear, and the remainder has to be smaller than that, what's smaller than degree 1?
Degree 0.
Degree 0. And what is degree 0?
0? No. It's just 1, right?
Well, what's an example of a polynomial that has degree 0? A constant. Any constant. So if you divide by something linear, your remainder will always end up being a constant. Just a number. Because it has to be a degree smaller than that. And if you go smaller than linear, you're at the constant. Okay, so here's an example tying in the formula that we have right here, which is very general. It's just very general. It applies to everything. Now I'm going to apply it specifically to dividing by something that's linear. Okay, dividing by something linear. So, if you divide f of x by h of x, you get denominator times quotient plus remainder. So if I divide f of x by h of x, and again, this time we're going to assume we're dividing by something linear. F of x can be anything you want. Then the numerator should equal denominator times quotient plus remainder. Numerator equals denominator times quotient plus remainder. Same formula I had up above, except this time the denominator is something specific.
What is this? This constant?
Yeah, I divide by like x minus 3 or x plus 6 or x minus 7. You're going to be dividing by something like we did in the very first problem. X minus 3. That's an example of dividing by something linear, and you ended up with a constant for your remainder. Okay, so now I want to look at that formula. And I want to focus on this right-hand side. And I want to know what f of c would equal. Well, this means to take all your variables and replace them with whatever inside there. So let's let x equal c. And I want to know what happens here. Watch what's going to happen. If you change all your x's to c's, you would have this. F of x equals this formula. F of c would equal c minus c times q of c plus my remainder. But what happens here when you plug c in for x? You just get the remainder. So what this means is if you're dividing by something linear, like this. Let's go back to this one. The first one. If I wanted to know the remainder to this problem, all I have to do is take the number that comes after the minus sign, take the c value, and plug it in to the original numerator. If I plug in c into the numerator, it will automatically give me the remainder. Let's try it on the first one. Let's plug 3 into this problem. And that 3 is the number after the minus sign. What's 3 cubed? 27.
Yeah, that's what I meant.
What's 8 times 3? What's 27 minus 24? And what's 3 plus 3? 6. So, plugging in the number after the minus sign into the original problem gives you a quick way to find out the remainder. What good is that? A lot of times, all we want to know is the remainder and if the remainder was 0. So now we have a quick way to find the remainder to a problem without having to do the entire problem out. Okay, and that's called the remainder theorem. The downside is it only works if you want to divide by something linear. If you want to divide by something with x squared and you want to know the remainder, well, you got to do the whole thing out. But if you have anything in the top and you divide by x minus, put some number in that box, you can find the remainder very quickly. Just plug the number in that box into the formula in the top, and it will give you the remainder. And that's, I tried to explain the reason why. So let's do this problem, and I want to find the remainder when you take f of x and divide by h of x, and then separately f of x divided by g of x. But don't do the whole problem out. I don't want to do long division. I don't care about the quotient. Let's say that this question said determine if h of x is a factor of f of x. If that was the question, you would do what we're going to do right now. Find the remainder. If it comes out to 0, it's a factor. If it doesn't come out to 0, it's not. Okay. So, in this topic, what number would you plug in? What number would you plug into your numerator? F of x is your numerator. To find the remainder when you divide by x minus 3. Plug in 3. 3 cubed is 27. 3 squared times 2. Plus 3 minus 5. What's 27 minus 18? 9 plus 3. And what's 12 minus 5? 7. So what does that tell you if you divide f of x by h of x? What does that tell you about h of x? It's not a factor. If you're trying to factor f of x, h of x is not the way to do it. Let's look at g of x.
Wait, why did we only plug? Why did we only use the 3?
Because the number that you want to fill in is the number that comes after the minus sign. So be careful with this one. Think of it like this. X minus minus 1. What would you plug in into the numerator to quickly just get the remainder? Negative 1. Negative 1 cubed is, what is it? Negative 1 minus, what's negative 1 squared? Times 2. Plus negative 1, so just minus 1 minus 5. Negative 1 minus 2. Minus 1 minus 5. So what does that tell you about g of x? It's not a factor. So finding a remainder is very useful to quickly determine if something is a factor. Any question on that? Yes, thank you. Okay, so we're going to pause there. Okay. So we just talked about what the remainder theorem was. Gives us a quick way to find the remainder. Well, kind of a small extension to that is the factor theorem, which basically says specifically, if the remainder comes out to 0, then we know it's a factor. Okay, so the factor theorem basically saying if you divide by x minus c, then that number you divided by will be a root of the polynomial, because you'll be able to plug it into the numerator and the answer will come out to 0. Anything that you plug in and the answer comes out to 0, we call that a 0. Okay, so if you find a number that is a 0 of the polynomial and you divide by that number, x minus that number, it will go in without a remainder and it will be a factor. Okay, that's called the factor theorem. So let me show you with an example, and then we'll go through. Okay, so this says use the factor theorem to show that x plus 2 is a factor of that polynomial. That basically means use the remainder theorem and show that you get a remainder of 0, or show that when you plug negative 2 in for x, that it is a root of this polynomial. If it's a root, then we know that the remainder would be 0. Because when you plug something in and it's a root, it comes out to 0. All right, so what number would we plug in to this bottom polynomial to find the remainder when you divide by x plus 2? Yep, negative 2. So plug in negative 2 into the bottom.
Wait, why negative 2?
Because it's always the number that would come after the minus sign.
Oh, that's right.
So in this case, think of it as x minus minus 2. And what are we hoping for this to come out to in order for x plus 2 to be a factor? We're hoping it comes out to 0, which would also mean that negative 2 is a root, because that's when you plug in a number and get 0. Let's see. Negative 2 cubed. Negative 8. Negative 2 squared times 5 is 20. 5 times negative 2 minus 2. What's negative 8 plus 20? 12. Minus 10 minus 2. 12 minus 10 is 2. 2 minus 2, 0. Yep. So we just proved several things that are equivalent. We proved negative 2 is a root of that polynomial. By proving it was a root, the number that we got for the answer is also the remainder when you do long division. We got a remainder of 0, which means that x plus 2, hope you feel better. So since we got a remainder of 0, that means x plus 2 is a factor. So if you wanted to factor x cubed plus 5x squared plus 5x minus 2, one of the factors is x plus 2. Well, there's something else. We're not going to go through that part, but if you knew that this was a factor, what do you do to find the other factor? Long division, right? If I, like the number 12, if this was the number 12, then I told you 3 is a factor. Well, then you can find the other one by dividing 12 by 3 and get 4. To get the other factor here, you would have to do out the long division. We already know the remainder would be 0. What we're really interested in be is the quotient. The quotient is the other factor, which would be a quadratic. So any questions on how we figured out x plus 2 as a factor? So, a bunch of equivalent statements, and I keep saying these things almost the past 2 or 3 lessons every time. Let's say you find a number that is a solution to an equation, and when you plug that number in, it gives you 0. So here's an example. In that particular case, the C value would be 2. 2 is a solution to this equation. It also means that 2 is a 0 of that equation. It's a number I could plug in for x and get 0 for y. It also means that 2 is a root of the equation. 0 and root are synonyms. They mean the same thing. But this next one, this is the one that's important. I want to go back and look at the problem we just did and see if we can figure out a pattern. In the problem we just did, we showed that negative 2 was a root of the polynomial. Negative 2 was a root. What was the factor? X plus 2. So now, if C is a root to a polynomial, then what must be the factor that it came from? Yeah?
X minus C.
Exactly. X minus C. That's very important. So if you find a number that is a root of a polynomial, then you know x minus that number is a factor. And what else happens graphically at the number C if you draw the graph out? A root is really a what when you see it as a picture? It's where it crosses the x-axis. So every one of these things means the same thing. It's just different ways of saying it. Roots, zeros, x-intercepts, factors, it's all the same. So what we can do now is work backwards, and I could give you a problem like this. I want you to find a third-degree polynomial that has those numbers as its zeros. I want these numbers to be the roots. I want those numbers to be the x-intercept. But the most important thing is working from these numbers to figure out the factors. Since it's a third-degree polynomial, it will have how many sets of parentheses? 3. And remember, each one of them is of the form x minus the root. And we know the roots. So what would the first factor be? And the second one? And the third one? Yeah. So what we could do is let's distribute that out. So we get x squared minus x plus 2x is plus x minus 2. Double check me on that. I think it's right. And then times x minus 3. And do it one more time. X cubed, x squared minus 2x minus 3x squared minus 3x plus x. So let's see. X cubed, x squared minus 3x squared minus 2x minus 3x plus 6. If we did everything right, and I graphed that, it should cross the x-axis at negative 2, 1, and 3. Well, let's see. So we've got x cubed minus 2x squared minus 5x plus 6. Since it's crossing at negative 2, 1, and 3, standard window is fine. Let's see if those values match up. Does it look like it crosses at
No.
why did I switch them? Let's see what happened here. Let me double, I must have foiled it wrong. So x plus 2, x minus 1, x minus 3. That is correct. Actually, let me make sure I typed in our answer right. That would have been a stupid mistake. X cubed minus... Always check to make sure you type the answer in right first. Okay, let's try that. Oh.
It's like the same. Oh, okay.
Yeah, it's slightly different.
Got it.
So negative 2, 1, and 3. Does that look good?
Yes.
Yeah. So that's how you can generate a polynomial and make it cross the x-axis wherever you want. You set up the factors and FOIL it out. You wouldn't have to FOIL it out for anything beyond a cubic. Okay. Questions on that? And last one. So finding zeros by factoring and then finding zeros by the graphing calculator, which we've done before. But let's try this. I don't think we've reviewed this in this class. Okay. When you have 4 terms, factor by grouping is one way you can do it. To factor by grouping, you take out what you can from the first 2, and then take out what you can from the second 2. So look at the first 2. Is there anything that they have in common? X squared. If you take it out of the first 2, what are you left with? X plus 2. Now, the goal is to factor something out here and hopefully end up with another x plus 2. What could we factor out? We could try factoring out a negative 4. And what would that leave me with? X plus 2. This is how factor by grouping has to work. You get the same thing. Now, what does that and that both have in common? So now factor that out. What's left with the first thing underlined in red if you factor out x plus 2? And what's left with the second thing?
Minus 4.
Minus 4. And x squared minus 4 is a difference of 2 squareds, so that factors again. How does x squared minus 4 factor? X minus 2. X plus 2. So, what values could I plug in for x that would give me 0? 2 and negative 2. You don't have to tell me that you can plug negative 2 in twice. It's negative 2, 2, and negative 2. What's happening at negative 2 is that's called a repeated root. But you don't have to tell me that it happens twice. Those are the numbers you can plug in. And that's how you find the zeros with factor by grouping.
Right, sorry.
Yes, in one second.
How did you get to the second line again after the first?
The one in red?
Yeah.
So to get to this one, we factored the GCF out of these 2, which was x squared,
Oh.
and then out of these 2, which was negative 4.
Okay.
So then if you factor an x squared out of the first term, you're left with x. And the second term, you're left with a plus 2. And then here, if you factor out a negative 4, you're left with an x, because you can distribute it back out and check. And negative 4 times positive 2 is negative 8.
Okay. Thank you.
Yes, you're welcome.
Where did you get the x squared minus 4? In the second
Here?
step?
So if you take the x minus 2 out of that thing underlined in red, what's left?
Oh, okay.
x squared. And then if you take it out of here, minus 4. Other questions on factor by grouping? Factor by grouping doesn't always work. The numbers have to be set up special for that to work. And then finding zeros on a calculator.
We can do that.
We can, yeah, we have, that's our last one. So you type it in, 2x cubed minus 4x squared. And how many times am I looking for it to cross the x-axis at most?
3.
3. So what I'm looking for is basically one of two things to happen in the middle of this function. It's a cubic. It's either going to turn and do something like that, or it's just going to have a bend. I need to find the bend or the turns. Until I find those, I don't know how many times it crosses. Or, yeah, that's what I'm looking for. One of these two things. Okay, let's try Zoom 6. Make sure we typed it in right. Is that a good window?
Yeah, that's not bad.
That's fine. Yep. So, where does it look like the 0 is? It looks like it's at 2. We could try to take a shortcut and quickly guess the answer is 2. Hit enter, and we see that yes, it was. Okay, in this case, I hit trace, and trace lets me move the cursor anywhere I want on the screen. So I hit 2, I hit enter, and I could quickly see the point. Yeah. Now, if it wasn't 2, like let's say it was like 1.99, then we wouldn't have got 0. So how would we calculate where that root is if we had to? Yeah.
You would go to second calc and then 0.
Yep. And then we pick a point, left, right, and guess, and we can see that that does confirm that the root is at 2. Okay? And that's how you find the zeros graphically. A lot of times if they ask you to find zeros graphically, it's going to be because it's not a nice answer. This one happened to come out with this. Okay, any questions on it?
Still not super comfortable with the long division.
The long division? Well, we could do one that's in the homework if you want. We do it together. Let me put the homework up first. And then if we do it together, you can practice it on your own. For this middle part, I could shorten that to just say 9, 11, 13, 15, 17.
Just say 9 to 21 on.
I must have changed it. Oh, what was that one?
6.
6. That's simpler to write down. So I'll do the whole thing, but we could just start. Find the quotient and the remainder. This is number 5. 2x squared minus 3x plus 1. And it says to divide that by x minus 2. Okay, so actually we can probably just do the whole thing. It won't take long. First thing you do is make sure you're not missing any terms. Squared, linear, constant. Okay, we're good. Divide x into 2x squared, and what do you get? 2x. Now multiply it back out. What's 2x times x?
2x squared.
What's 2x times negative 2?
Negative 4x.
Negative 4x. Subtract. These are gone. What's 3x minus minus 4x? X. Bring down your next term. The degree here is a 1. Degree here is a 1. You got to go one more time. What's x divided by x? 1 times x. 1 times negative 2. Subtract. And what's my remainder? 3. So is x minus 2 a factor? No, because we got a remainder of 3. Now, I could have found this remainder very quickly by just plugging 2 in. What's 2 squared?
4.
What's 4 times 2? What's 3 times 2?
6.
8 minus 6? 2 plus 1? There you go, there's your remainder. So that's a quick way you can check if you did it right. But that's how you do the long division, and that's how you can check your remainder. So it just takes a little bit of practice. But we can go over some more when we do the homework. So now you don't have to do number 5. So it's 4, 6.